All right, now we're going to talk about file systems and a little bit more in depth about some of the file systems. There are several different types of file systems out there, but we're going to focus on NTFS, ext4, and FAT32 for all of this. So first off, what is a file system? Well, it's going to be the software layer that organizes, names, and tracks where data is stored on the physical storage media. A file system sits on top of the physical media and is used by the operating system to view all the data and organize it in a logical and understandable method. So you have your physical media. So this is going to be like on a CD or DVD, that's going to be your physical optical disc. On a solid state drive, that's going to be the chips on there which stores the actual zeros and ones, if you will. On a mechanical disk, that's going to be the platters that hold the magnetic field of the actual data there. And so on a disk itself, the raw addressable units is going to be the sectors and clusters. So every drive will have a certain number of sectors, and those will be grouped into clusters. The typical sector size is 512 bytes for each sector. So you can kind of do the math to compute how many sectors there are given the total size of a drive itself. On top of that is going to sit your file system. This will have your file allocation table or your file table, or it could be a inode table, which that is used for ext4 and other Linux type file systems. The MFT is used by NTFS. The FAT table is used by FAT32 and other similar ones. But the structure for that is kind of a database or a listing of where each file begins and metadata for the file and other pieces of information which goes along with that. The operating system file API has things like create file, open, read, write, and this is a way that you can program access to be able to create a file or read the contents of that. And what happens is when you make a call to the operating system API, that will then go to the file system itself, request the file, and then the pointer to the file, and then the information will get returned through that API to the calling program. At the bottom level of that, or top level, depending upon which direction you look at this, is the user application. So any program which can interact with files will be an application, which then goes through the API, which then goes to the file system, which then goes to the specific grouping of sectors on the disk, which will then go to the physical media and retrieve that data, and it would work its way back to the application. So forensics analysis works at that file system layer and below, the sectors and clusters and physical media. There is big section of digital forensics, which is recovering the physical magnetic fields from a disk or trying to access the physical storage that was on there without having to go through a file system. That typically requires very specialized equipment and specialized processes and is not a trivial method. Most digital forensics will operate more at the file system level or the sector level to create an image of that and then analyze that particular data. So NTFS stands for New Technology File System. This was created by Microsoft back in the 90s, and it originally was their enterprise style operating system and file system and everything else. Nowadays, Windows, pretty much all Windows systems use NTFS for their particular file system. You have at the beginning what's known as a MFT or a master file table. This is a database of every file and directory on that volume. And each MFT has, or entry has 1 kilobyte in size, which contains the metadata, which is size, timestamps, which is created, modified, accessed, and changed, permissions, data location, deleted records, will remain in the MFT until it becomes overwritten. So that's one of the key things, especially with digital forensics, is as data is deleted, typically it gets marked as deleted but doesn't get freed up or reallocated. That information may still exist on that file system somewhere, which is why when you take an image of a drive, you want to take an image of everything and not just whatever's been allocated or whatever is visible to the file system. The timestamp, so every MFT entry stores 4 timestamps per file. There's the standard information, which is visible to user, and then the file name, which is forensically significant, and it is a timestamp which is not able to be modified by a user. It's visible at the kernel level, but a user typically wouldn't be able to go in there and modify that particular timestamp. Whereas the standard information timestamp is visible to a user and can be manipulated. So timestamp analysis, timelining is one of the big things on file system analysis, because when you're looking at the timestamps, the ones which are hard to fake or modify typically have a stronger impact on your overall timeline. There's also what's known as alternate data streams. And so this is a process to where you can have a named file and then you can add an alternate data stream to that file. So according to the operating system, when it reads the file, when it sees the file, it sees just that file, but then it loads the data stream afterwards. It's useful for malware to hide its entry point or hide its data using those alternate data streams. And it's not visible to an end user in the operating system typically. So forensics tools can see those alternate data streams and can recreate the information. And so that's a way that a skilled malicious individual could try to hide data, which a forensics tool would enable someone to see that data. The last part is journaling, and NTFS adds in all sorts of journaling so that when a file is deleted, it records that change and it maintains that for a certain length of time. In the past, when you had a file system without journaling, if you were writing or changing a file and you lost power or something happened, that file would become corrupted because it was a write at that specific time or a change at that time, and it didn't maintain a log of what was happening. Now with modern journaled file systems, which NTFS is one, ext4 is another one, then it writes the information to a journal and then it performs the action on the drive itself or on the file system. That way, if there is any sort of power interruption or any sort of issue, then the journal could roll through the information again without losing any data. Now, because it maintains a copy of all of that in a separate journal, that journal is a place that is recoverable through forensic tools. So being able to view the journal and analyze whatever is in the journal is very valuable to recreating an entire picture. ext4. This is the extended file system version 4 for Linux. This is one of the more common Linux file systems which are out there. There are lots and lots of different file systems, but ext4 is typically the one that you would run into. This one, when it stores a file, it stores it with what's known as an inode. And that inode is a number that links to a specific starting point on the file system. Every file, every directory has an inode. And typically will have a unique inode, although depending upon what you're actually doing, you can create what's known as hard links to where two files share the same inode. That just means that they are pointing to the exact same location, the exact same data. But every data and unique data point will have its own unique inode. So the inode will have information in the metadata, such as permissions, the owner of that particular inode, timestamp, size, pointers to various data blocks. It doesn't contain the file name, but it does contain a lot of other relevant information with that inode. On Linux, there is a command called stat, S-T-A-T, and that will show you quite a bit of information that is stored in the file system related to that particular object. The ext4 volume divides it into block groups, each containing a copy of the superblock, which is the metadata for that, the inode table, and the data blocks. There is, depending upon the file system, and I believe ext4 doesn't create backups of the superblock, but other file systems may create backups of the superblock, and that way if the drive gets corrupted, then you can recreate the partition and file system layout from a backup somewhere else on that particular drive. Most forensic tools would have a method and a way of verifying the metadata and the superblocks to ensure that it is consistent across all of that and hasn't been changed or tampered with or modified. ext4 also includes journaling. I already talked about that with NTFS, but the journaling for ext4 is relatively robust, and it does keep a log of any recent operations, and it will be able to roll through those operations if they had failed for some reason. When you delete a file, the inode is marked free, and the entry is removed, but the data blocks are still there. Really, all it does is just kind of remove that entry point to the file or the object. So the file system, when it goes to allocate a new block of data, it starts at the next available inode, which could be the previously deleted one. And so those data blocks may be there until they get overwritten. This is why in the case of disaster recovery, or if someone had deleted data from a system, you make sure that the system is secured and powered off, because you don't want any changes to the particular file system that may overwrite any deleted blocks. FAT32. This one is an older file system, and it's not in use as much anymore. This was on Windows, the precursor to NTFS for consumers. A lot of, I believe that file system or operating systems prior to Windows XP used used FAT32 by default on the consumer versions. Nowadays, everyone uses NTFS just because it is so much more feature-filled and robust and reliable, and it also supports larger drives. FAT32 does have a limitation on the actual file system size and the drive size and individual file size, and so there's a reason why it's not used as much. Where it still does tend to get some use is removable storage, such as USB thumb drives, cameras, older storage media. So as digital forensics, you may end up getting a like a camera SD card, or an older camera SD card, or even other storage type medias like compact flash or something of that nature. And those being small enough and the camera maybe being rudimentary enough, it may use FAT32 by default because that's the only file system that it actually understands. So understanding what FAT32 is and why it is, or it was so popular and still remains popular to this day, is important. So kind of the volume structure of it is, at the beginning you have the boot sector, which will contain the volume labels, cluster size, your file allocation location or your FAT table location, and then you will have 2 copies of it, just in case one gets corrupted. Each copy will have the clusters that belongs to each file, as opposed to just like an inode and metadata and that sort of stuff. The root directory is the fixed list at the top of the file levels or in the cluster change, depending upon if you're using FAT16 or FAT32. And then the data area will be the actual files stored in those particular clusters. So deleting happens a little bit differently. So when a file is deleted, the first character of that entry is replaced with the hex 0xE5, or literally the hex E5, which is the deletion marker. So that marks it as freed, but just like everything else, the data tends to persist along there until it gets overwritten by a later process. There is no journaling, so corruption has happened and does happen with FAT32. So typically what you need to do is you need to make sure that no changes are made as you're doing a forensics analysis, which is where you end up adding in a write blocker or something else to prevent changes to the particular disk. There are timestamp limitations, so it'll only store the created, modified, and access timestamps, and it only keeps day timestamps and local time, but it doesn't store it in a UTC format or anything other than that. It's just very rudimentary, and it comes from a time back in the 80s and 90s when this wasn't as critical of a thing. It was important to have a time, but it wasn't as important to identify the particular time zone, just because the internet wasn't as widespread as what it is now, and time zones didn't really matter as much. So just kind of a very quick comparison between all of them. FAT32 is the smallest of them because it has a 32-bit addressing scheme. It is very cross-platform. I mean, pretty much any operating system understands FAT32 natively. The maximum file size is 4 gigabytes in size with a maximum volume of 8 terabytes. I believe that there's a 4 terabyte limit as well, and I can't remember exactly what that 4 terabyte is. There's going to be a power of 2 limit for all of this stuff. Doesn't support journaling, doesn't support access controls, doesn't support encryption. Encryption on a FAT32 system is, or a FAT32 file system, is typically handled through third-party programs and processes, but that's not nearly as common. The deletion is you look for the hex E5 marker at the beginning of entries, and that will indicate that it was a deleted file or a not deleted file. And then there are only 3 timestamps which are stored with each of the file, just a date and a simple time. ext4, that's primarily on Linux, and it's one of the more common versions out there. There were 3 other versions that came before it. Old versions of Linux used ext2, and that one was a non-journaling file system. Now ext3 and 4 added in journaling and all sorts of other protections and benefits. So that is one of the more common file systems that you will encounter, especially from a Linux system. The maximum file size is 16 terabytes per file. The maximum volume size is 1 exabyte in size for an entire volume. So you can get really, really large storage sizes. It does support journaling, does support what's known as POSIX, or the Portable Operating System Information Exchange. And this is a standardized way of passing information across different versions of Linux that will maintain the same each time. Encryption is handled through what's known as dmcrypt. There are other encryption schemes and encryption methods. That's just one of the built-in Linux versions for it. When data is deleted, typically it's the inode which is removed, and the actual data blocks still reside on that file system. And it does store many forensic timestamps for all of this. The last one that we talked about was NTFS. Again, this is Windows primarily. Linux does have NTFS support that can be added in there. For a while, it was very buggy. Nowadays, it's not as buggy, but generally, if you need to look at an NTFS file system, you use Windows. If you need to look at an ext4 file system, you use Linux, because Windows doesn't play nice with the Linux file systems. Maximum file size, 16 exabytes. I'm not sure if that's entirely correct because the maximum volume size of 256 terabytes. I'll have to double check those numbers. But it does support large files and large volumes, although generally that's more for research locations and large storage locations. It does support journaling, supports a full access control list. In fact, Microsoft's access control list is really robust and very granular when you go to manage and maintain access and permission to various folders and objects. It does support encryption through BitLocker. On Windows these days, that's built into, like Windows 11 requires BitLocker by default. Prior to Windows 11, it was a thing that could be turned on. It would work with NTFS systems. It didn't work with other file systems, but it does support encryption and full disk encryption. Again, with deletions, it's the file table that it removes that entry there, but the actual data still exists on the particular drive. So again, the key takeaways from this, file system determines what metadata survives deletion. Choosing the right analysis approach requires knowing the targeted file system. So if there's journaling enabled, if there's the Linux system, if it was Microsoft and you needed to look through other specific attributes, it just kind of determines what approach you end up taking. The NTFS entries and dual timestamp sets both of those attributes, and the file name one is maintained by the kernel and can't be modified by users without quite a bit of effort. So generally that would be the more reliable timestamp location. And if there is a discrepancy between those two, that could be used as an indication that something has changed or something has been modified. ext4 nodes and USN Journal provide equivalent Linux forensic capabilities. Again, deletion doesn't immediately destroy the data. FAT32 just marks the beginning of the file with the hex E5. So recreating that is not too terribly difficult, assuming that the information hasn't been overwritten. And file system structures, not just file contents, are evidence. So you need to understand that format before the analysis.